All right, today's lesson is going to be about us learning how to use a new format for drawing atoms. In our previous lessons, we've learned a method called the Bohr model, in which you have to include things like the nucleus, to include how many protons there are, how many neutrons there are, and you have to draw every single electron on every single shell. Today, we are going to learn a way that is a lot more simple and just a different type of useful. It's very useful for bonds only. It is not useful for giving us as much information as a Bohr model would, but it's very good for ionic bonds and for molecular bonds, which are the past two things that we learned about. So let's put it to use. Gilbert Lewis was a brilliant and influential American chemist who invented a concise method of showing bonding, and particularly covalent bonding. And this method is called a Lewis diagram, or we call them a Lewis dot diagram. It's a diagram that illustrates chemical bonding by only showing two things. It makes it way simpler. You only have to show an atom's valence electrons, so its outer shell electrons, and an element's chemical symbol. So just the valence electrons and the chemical symbol. Sometimes we have different names for them. Like I said, we either call them Lewis dot diagrams, Lewis diagrams, Lewis structures, or electron dot diagrams. So today's lesson is going to be pretty brief. I'm just going to show you how you should go about drawing these diagrams. Here are the rules. The first rule: dots that represent the valence electrons, those outer shell electrons, are placed around the element symbols at points of the compass. So what I mean by that is I initially want you can place your dots at the top and the right and the bottom and the left, north, east, south, and west. Electron dots are placed individually until the fifth electron is reached, at which point we start making pairs, right? If I had, say for example, I had, let's go with, what's one that I could use? Oxygen. So oxygen, I'll draw the chemical symbol, will be O. And I start placing my electron dots. So there's one, there's another one. These are not great dots, but you get the idea. There's a third and a fourth, but we know oxygen is in group 16, so it's going to have 6 outer shell electrons. So I've done 1, 2, 3, 4. I got to start pairing them up. 5 and 6. So there you have it. That's it. That is what oxygen's Lewis dot diagram looks like. There's no rule for where you technically need to start. You can start north, east, south, or west, but you might find it easier to just be consistent and always start from that north position. Did I go too quickly there? I feel like I might have gone too quickly. Okay, well, you can pause if you need to. Moving on. It's really that simple. It's really that simple. It's just the chemical symbol surrounded by however many outer shell electrons it has. So I want you to spend the next little bit here practicing on your own. I'll do the first 3 for you. There they are. Hydrogen it's in group 1, so it has 1 outer shell electron. Lithium is in group 2, is also in group 1, so it also has 1 outer shell electron. Helium has 2, and then beryllium, which is in group 2, has 2 outer shell electrons. Now, just an interesting part, right here, we're skipping the transition metals. Okay, so we're skipping where the transition metals would normally go, and we're moving on here to boron. So then boron is in group 13, so it has 3. And at this point, I'll ask you to pause the video and try to fill out the rest of the table on your own. So if you pause the video and you're back now, I will put up the answers. You've got carbon, C, which is in group 14, so it's at 4 outer shell electrons. Nitrogen, which is an N, and it's got 5 outer shell electrons. Oxygen, which we drew on the last page, has 6 outer shell electrons. Fluorine has 7 outer shell electrons, and then neon, Ne, has 8 outer shell electrons. And then we just move to the next one. And what you'll notice here about this is, yeah, it's not telling us quite as much information as a Bohr model because these three all look the same. Now, in terms of their chemical reactivity and some of their chemical properties, sure, they are the same. So that makes sense that they would look the same. However, it doesn't show us the total number of electrons. We obviously have way more electrons in sodium than we do in hydrogen, and way more protons as well, and a much higher mass. But we don't need that for bonding. It's not as important for us. So look, you'll notice that the electron formations will all look going down. The only one that looks different from where it is helium here. It only has 2, and then neon and argon will have 8. That's because helium, you skip this whole kind of row here where they normally would count up by 1. Helium ends up way over here. It technically has a full outer shell because the first shell only has a max of 2 electrons. So let's move on. You can follow these rules that I'll mention here to draw ionic compounds. So now we're learning how to draw, we learned how to draw ionic bonds with Bohr models. Now we're going to draw ionic bonds with Lewis dot diagrams. So what ends up happening is the exact same idea. Positive ions, which are the metals, and try to think right now, you can pause the video, try to remember what the name of a positive ion is. They get rid of their one outer shell electron, their one electron dot. It could be 2 as well. It could even arguably be 3. And it gets removed from the valence shell for each positive charge that the ion will have. This usually means that all of the electron dots are going to be removed. Now, if I showed you on that last, on that last slide, if I told you that sodium, for example, was getting rid of its outer shell electron. Well, if I get rid of an outer shell electron, sodium right here, if it gets rid of its outer shell electron, that goes away. Well, that's all that sodium is going to look like now, right? Sodium is literally just going to be its chemical symbol. So that's what it says. Only the element symbol remains. But what we need to do is, this is technically not right. This is not what sodium should look like. So we need to specify that we are showing sodium within an ionic bond. And we have to specify, okay, the square brackets tell us, just like they did with Bohr models, that we're in an ionic bond. And I also need you to tell me, okay, it got rid of an electron, so it will have a +1 charge. So now that is right. It looks weird with just having the symbol, but that is technically the correct way to show sodium when it's in an ionic bond. Make sure you put that charge at the top right. For negative ions, well, usually we're going to have an electron dot added to the valence shell. And this electron dot, there could be 1 or 2 or 3 again, for each negative charge of the ion. That's how many electron dots we're adding. So what this will mean now, if I go back to my same example, which was oxygen I used, oh, that is terrible, oh, but you get the idea. And oxygen has 1, 2, 3, 4, 5, 6, but we add another 1, 2 to make it have a full shell. Now, this doesn't look like a proper drawing. This is bugging me how badly I've drawn oxygen here. I'm just going to fix this. Okay. This does not look like how we know oxygen to look. Oxygen is only supposed to have 6. So again, we put square brackets around it to specify, okay, this oxygen is actually not an oxygen atom. This is an oxygen ion. It's part of an ionic bond, and it received 2 extra electrons. So that -2 tells us that. Okay, so generally with the nonmetals or the negative ions, which, remember, negative ions, I'll tell you now if you can try to remember the name. Negative ions are called anions. Positive ions are called cations. So for the negative ions, for the anions, we'll have full outer shells with negative charges. And for the positive ions, we'll have empty outer shells with positive charges. Let's draw the Lewis dot diagram for table salt. So if we are going to do that, just give me 1 second here. Okay, I was going to draw it on my paper. I do think for this one example, I can just draw it on the slide here. So we're going to draw the Lewis dot diagram for table salt. So what I need to think about is the fact that, okay, Na has one outer shell electron and Cl has 7. 1, 2, 3, 4, 5, 6. I'm trying to draw with my mouse here. This is why this looks so questionable. Okay, and then what happens is we have this electron transfers to chlorine, right? The one electron will transfer from sodium to chlorine. So there it is. Okay. Now what we can actually do is we can get rid of, like I did in my last example, we can actually get rid of that electron entirely. But what we need to do is just specify, okay, hey, I didn't actually make a mistake. I've done this intentionally. I am trying to tell you that this sodium is part of an ionic bond and it got rid of one electron, so it's got a positive one charge, and that chlorine gained an electron in the ionic bond and it is one negative. That is what, I mean, written nicer when you're using your pencil and your pen, but that is what your Lewis dot diagram for table salt should look like. So students are generally quite pleased to learn about Lewis dot diagrams because they are a lot quicker to draw than Bohr diagrams. So using what we just talked about, I want you to try magnesium oxide and barium bromide. So try that on your own, magnesium oxide and barium bromide. You can pause the video, and then when you come back, I will have the answers drawn out for you. Okay, so if you paused and you're now back, you can see that I've got the answer for magnesium oxide up there. Magnesium is in group 2, so it has 2 outer shell electrons, so it's looking to get rid of 2 electrons and gain a positive 2 charge. Oxygen is in group 16, 6 outer shell electrons, looking to gain those 2 from magnesium and will have a negative 2 charge. Now, we are in a little bit of an interesting situation here because barium can give 1 electron to bromine, but bromine can only take 1 of them, right? So bromine here is happy. Bromine here is done, complete, full outer shell, a -1 charge, and happy. But barium is not happy, right? Barium still has this leftover charge. So this is like that other example that we did with the Bohr diagrams, is that barium still has another electron that it's wanting to get rid of. So we have to introduce a second bromine atom in which barium can give its second outer shell electron to. So now this will come over here and we will have 3 happy ions now. Sound like Bob Ross. Okay, so we've got -1 and then barium got rid of 2 electrons. So it is 2 plus. So that's a really interesting example that you might see. An interesting thing that you might see in a question is that there is specific proportions in which these elements can react with one another. We, in this scenario, I'll just give you a hint at where we're going to end up moving with this. This right here is just 1 part magnesium, 1 part oxygen. That's what its chemical formula looks like. But barium bromide, Ba, Br, doesn't work because it didn't satisfy the barium. So in nature, we don't have 1 part barium, 1 part bromine reacting. We have 2 parts bromine, 1 part barium. So it would actually be BaBr2. That is the exact reason why we see compounds such as H2O, for example, or CO2. The amounts in which they present themselves is very, very important to whether that chemical reaction can actually take place or whether it even exists, because it wouldn't exist if they weren't in the proper amounts. So we're at the 15-minute mark here. I'm going to end this lesson here. So we'll do this one in 2 parts. In our next lesson, we will take a look at what it looks like to draw Lewis diagrams for molecular compound. We just did ionic. We're going to move on to molecular. Okay, we'll talk to you later.